All right, let's journey to the very edge of physics to talk about some of the most extreme, frankly bizarre objects in the entire known universe, neutron stars. And look, these aren't just stars. They're cosmic enigmas that push the laws of nature right to their breaking point.
So take a look at this number, 100 billion. It's just an almost impossibly large figure, right? So what in the world does it represent?
Well, that is the gravitational pull on the surface of a neutron star. 100 billion times stronger than what you're feeling right this second. I mean, if you could somehow stand on one, you'd be instantly crushed into like a stream of subatomic particles. And believe me, that's just the beginning of how extreme these things get. Yeah, this is where it gets truly mind-bending. The density is so completely insane that a single teaspoon of neutron star stuff would weigh as much as 7 million elephants. Just try to wrap your head around that for a second. It's almost impossible.
But it's not just about the density and the gravity. Oh no, neutron stars hold a whole bunch of cosmic records. Let's run through some of their most unbelievable properties.
So besides a black hole, they are the densest objects in the universe. They are the fastest spinning things we've ever seen. I'm talking rotating hundreds of times every single second. Their magnetic fields, quadrillions of times stronger than Earth's. And they are born in the trillion-degree fires of a supernova. I mean, they're really objects of superlatives.
So where do these cosmic monsters actually come from? Well, their origin story is every bit as dramatic as their properties, and it all starts with the violent death of a massive star.
You see, when a star that's way more massive than our sun runs out of nuclear fuel, its core just collapses under its own immense gravity. That collapse triggers a cataclysmic supernova. This explosion blasts the star's outer layers into space, and it leaves behind this absolutely spectacular remnant, like the Crab Nebula you see right here. And right at the heart of that beautiful chaotic nebula lies the collapsed core, the neutron star. During that collapse, the pressure is so intense that protons and electrons are literally crushed together, forming a super-dense ball made almost entirely of neutrons. We're talking about an object the size of a city, but with more mass than our entire sun. Okay, now for the really fun part. We're going to take a virtual trip, peeling back the layers of a neutron star to see what's actually inside. And let me tell you, it's a journey into some of the strangest physics you can possibly imagine.
Our journey begins at the surface. And here, we'd find this razor-thin atmosphere, probably made of hydrogen or helium. But just a few centimeters below that, reality starts to get very weird and very quickly.
We hit the crust first. The outer part is a solid lattice of atomic nuclei. But as you go deeper into the inner crust, the immense pressure contorts these nuclei into these bizarre shapes that physicists, and I love this, they call it nuclear pasta. Yeah, think spaghetti and lasagna, but made of nuclear matter. It's also here that we find neutrons that have literally dripped out of the nuclei, and they flow freely as a superfluid that's a liquid with zero friction. Wild.
Okay, plunging deeper now, we reach the outer core. At this point, the nuclei have completely dissolved, creating this uniform soup of particles. It's mostly neutrons, with a smaller number of protons and electrons, all existing in this strange quantum state where everything is behaving in these really interconnected ways.
We've now arrived at the very heart of it all, the inner core of the neutron star. And this, my friends, is one of the biggest question marks in all of physics. The pressures and densities here are so extreme, they go way beyond anything we could ever replicate on Earth. Our best theories of physics, they kind of break down, leaving us with this profound mystery, which is perfectly captured by this question mark in the diagram.
This is it. This is the question that keeps astrophysicists up at night. What state of matter could possibly exist under these insane conditions? We don't know for sure, but man, we have some incredible theories.
So there are a few competing ideas about what's going on. One possibility is that it's just an even denser form of neutron matter. Another is that the neutrons themselves actually transform into other heavy particles called hadrons. A more exotic theory suggests the pressure is so great that neutrons break apart, releasing their fundamental building blocks, quarks, to form this free-flowing quark-gluon plasma. And finally, some theories propose these exotic quantum states called boson condensates could form. Figuring out which one is correct is a huge goal of modern physics. So if we can't actually go there, how in the world do we study these things? Well, it turns out that many neutron stars send us signals, basically acting like giant lighthouses in the cosmos. Most of the neutron stars we found are what we call pulsars.
They spin incredibly fast, and they have these powerful magnetic fields that channel jets of radiation out from their poles. Now, as the star rotates, these beams sweep across space. And if one of those beams just happens to cross Earth's line of sight, our radio telescopes pick up a regular repeating pulse. Tick, tick.
And what you're seeing on the left is the actual chart recording from the very first pulsar discovery back in 1967. That rhythmic kind of otherworldly signal was so powerful that years later, the band Joy Division used a visualization of its pulses for the iconic cover of their album Unknown Pleasures. How cool is that? A signal from deep space immortalized in music history.
But these pulses, they're way more than just cosmic curiosities. They actually turn neutron stars into these invaluable laboratories for testing the fundamental laws of nature.
Because pulsars spin with such astonishing regularity, they are, without a doubt, the most stable clocks in the universe. By timing their pulses over years and years, we can test Einstein's theory of general relativity under conditions of extreme gravity. It's like a cosmic stress test that's way beyond anything in our solar system.
And it gets even better. By monitoring a whole array of these super precise clocks spread across the galaxy, scientists can search for tiny correlated disruptions in their timing. And what are those disruptions? They're the signature of gravitational waves. Actual ripples in the fabric of space-time itself washing over our galaxy. It's basically a galaxy-sized gravitational wave detector.
Which really brings us to our final thought. Neutron stars are cosmic laboratories, and they are operating at the very, very edge of our understanding. They are the crucibles where matter is forged into states we can only dream of. So, as we continue to listen to their faint, rhythmic pulses, they promise to unlock even deeper secrets about the fundamental nature of our universe. The real question is, what will they tell us next?